This video, we discuss problem 9.1.11-T from Essentials of Statistics, 6th edition by Mario Triola. The problem statement says, a study was conducted to determine the proportion of people who dream in black and white rather than color. Among 322 people over the age of 55, 63 dream in black and white, and among 310 people under the age of 25, 10 dream in black and white. We're asked to use a 0.01 significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 55. We're asked to complete parts A through C below, and part A asks us to test the claim using a hypothesis test. And then it says, consider the first sample to be the sample of people over the age of 55, and the second sample to be the sample of people under the age of 55. They say, in that case, what are the null and alternative hypotheses? In order to solve this together, I'll share my paper with you. Okay, so we've already identified population 1 and population 2. Population 1 is the sample of people over 55. The population 2 is the sample of people under 55. If I want to state the null and alternative hypotheses for this hypothesis test, I need to go up to my problem statement here and state the claim first. So it says use a 0.01 significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion of for those under 25. So if population 1 is the sample of people over 55, the proportion of people who dream in black and white for sample 1 would be denoted by p sub 1. And then the proportion for those under age 25 would be denoted by p sub 2. And this is saying that our claim is that the proportion of people over 55 is greater than the proportion under 55. So our claim is this. Since this does not contain the condition of equality, that makes that the alternative hypothesis. And the null hypothesis is going to look just like that, but instead of having this greater than sign, we're going to change it to an equal sign. So let's go to my lab statistics and identify this there. So we're looking for a greater than sign in the alternative, and of course an equal sign in the null hypothesis. Okay, so I think F will work. P1 is equal to P2, that's our null hypothesis, and P1 is greater than P2. That is our alternative hypothesis. Great. Now the second thing that we're asked to do here is identify the test statistic, and notice that we're asked to round to 2 decimal places as needed. So what I'll do is I'll show you how to compute this on my paper and also remind you of what this test statistic, represents in terms of the distribution of P1 hat minus P2 hat. Okay, so this is the formula that we're going to use for our test statistic. But before we apply this formula, I want to talk about what this represents. This is a z-score. This is a number of standard deviations above the mean, assuming that a certain distribution is approximately normal. And what we're interested in here, whenever we're dealing with a hypothesis test about 2 proportions, is the distribution of P1 hat minus P2 hat. So we're imagining we create a bunch of samples of the same size, and then we come up with a distribution of P sub 1 hat. And then we do the same thing for P sub 2 hat. We have a bunch of distributions or a bunch of samples of the same size, and we're computing those P sub 2 hats. And then we subtract them. And then we're looking at the distribution after we subtract. Well, it turns out that if P sub 1 hat and P sub 2 hat both have normal distributions, the distribution of P sub 1 hat minus P sub 2 hat will also have a normal distribution. And the mean of the distribution of P sub 1 hat minus P sub 2 hat is equal to the difference between the true population proportions, P sub 1 and P sub 2. Now, whenever we are converting to a test statistic, we're saying, okay, let's assume that the null hypothesis is true. And whenever we're testing claims, at least in this class, about 2 proportions, we're always assuming that P1 is equal to P2. Or in other words, we're assuming that P1 minus P2 is equal to 0. So we're saying, assuming that P1 minus P2 is equal to 0, which is the same as assuming that P1 is equal to P2. so that the mean of this distribution of P1 minus P2 is 0. How many standard deviations above the mean or below the mean is the value of P1 minus P2 or P1 hat minus P2 hat from our samples, the two samples that we have. How many how many standard deviations above or below the mean is that value given that assumption? In order to figure that out, we're going to compute P1 hat and P2 hat and take their difference. So that's going to be x1 over n1 plus x2 over n2, where x1 and x2 are the number of successes in each sample, and then n1 and n2 are the sample size for each sample. Now, what we're considering to be success here is a person that dreams in black and white. So in our first sample, that's a sample of people over 55, we had 63 that dreamt in black and white, and the sample size was 322. Oops, I put an addition sign there. I meant to subtract those. Now for our second sample, we had 10 that dreamt in black and white, and there were 310 in that sample. So if we take the difference of these, that's our P1 hat minus P2 hat. Let's see what that is. Just approximately. So I get this 233 over 1426, which is an exact answer. But to get a decimal approximation, I'll just press this SD button on my calculator, and I get about 0.163 as that difference between the two sample proportions. So we're saying if the mean of this distribution of P1 hat minus P2 hat is equal to P1 minus P2, and it is, and that is assumed to be equal to 0. How many standard deviations above the mean is this P1 hat minus P2 hat that we have from our samples? So we'll have P1 hat minus P2 hat here, which is approximately this 0.163. And we're saying to ourselves, is that a significantly high or significantly low, or in this case, significantly high value of P1 hat minus P2 hat to have, provided that the null hypothesis is true? In order to figure out if this is significantly high or significantly low, we're going to take this distribution of P1 hat minus P2 hat, and we're going to convert to a standard normal distribution. So we're converting from this over here to another distribution over here. Now, the mean is still 0, but now we're looking at z-scores as opposed to these values of P1 hat and P2 hat. Now, whenever we're converting from an x value to a corresponding z-score, what we typically do is we take that x value and we subtract the mean and we divide by the standard deviation. That's exactly what we're doing here, but instead of an x, we have the difference between P1 hat and P2 hat. And then the mean for this distribution is assumed to be P1 minus P2, but under our assumption that the null hypothesis is true, this value is just 0. And then the standard deviation is approximately given by this expression down here. That's the standard deviation of this distribution. Now, if you're wondering to yourself, why on earth would that be the standard deviation of this distribution? It has something to do with the variance. It turns out that there is a fact, a property of variance. If you have two independent samples and you're looking at the variance for the difference between those two samples, it turns out that you actually just have to add the variance of the samples. You're saying, what? I know, it seems odd that you would subtract here and add here. But that's actually how it works. And the variance for P1 hat, if we are assuming that, well, P1 hat is an unbiased estimator of P1. This is equal to P1 times Q1 divided by the sample size. And this is also equal to P times Q divided by N. But of course, because we're talking about our second sample, we'll use P2, Q2, and N2. So that's variance. Now, if I want the standard deviation, I would have to take the square root of both sides. So this, in general, would be assumed to be this. But if I want to use this formula, and we're making the assumption that the null hypothesis is true, we're making the assumption that P1 and P2 are equal to each other. Now, we don't actually have the value of P1 or P2 here at all. All we have are P1 hat and P2 hat, but we're assuming that P1 minus P2 is 0, which is the same as assuming that P1 and P2 are equal to each other. So you might say, well, if I'm assuming these are equal to each other, what is our best guess for the value of P1 and P2? If they're equal to each other, it's going to take on one value rather than these two values that we have in this formula. Well, our best guess of what P1 and P2 would both be at the same time is given by what's called the pooled sample proportion. So this is the proportion that we have in a larger sample. So instead of thinking of this as two samples, a sample of people over 55 and a sample of people under 25, and then looking at the proportion in each group that dream in black and white, we're going to say, let's not discriminate by age. Let's think of them all as people in our sample and calculate P bar. Now, P bar is going to have the number of people that, or is going to be given by the number of people that dreamt in black and white, or who dream in black and white, divided by the number of people in this larger sample where we're not really discriminating by age. We're not grouping them according to their age. So in this case, X1 and X2 are equal to 63 and 10. So we're going to add those together. And our two sample sizes were 322 and 310. So it looks like we've got 73 people that dream in black and white, and 632 of them, or out of the 632 people, total that we have. I'm sorry if you guys are distracted. My mom is playing the piano and I think it's really beautiful, but it makes it a little bit hard to concentrate. I'm doing the best I can. So we've got this P bar here, and that's equal to this, and P bar is that assumed sample proportion. So we're going to say that because we're assuming that P1 and P2 are equal to each other, the best guess of what P1 and P2 are is this pooled sample proportion. So then rather than using P1 and P2 here, which are unknown, we're going to use this estimate of P bar here. And then Q bar is exactly what you would expect. If P bar is the number of people who dream in black and white over the total number of people, Q bar is the number of people that dream in color over the total number of people. And that's the complement of that. So we're going to have 1 minus 73 over 632, which is 559 over 632. So those are the values, P bar and Q bar, that we're going to use in this formula. And that is the estimated standard deviation of this distribution over here. And we're using that estimate, again, because we're assuming that P1 and P2 are equal to each other. And the best guess that we have for what P1 and P2 are equal to is this P1 bar, or excuse me, is this P bar, not P1 bar. So we've got P bar Q bar over N1 plus P bar Q bar over N2. And that's our standard deviation. So I'm taking my continuous random variable p1 hat minus p2 hat, and then I'm subtracting the mean of the distribution of p1 hat minus p2 hat, which is equal to p1 minus p2, which we're assuming to be 0 because we're assuming that the null hypothesis is true here. And then we're saying, okay, if the null hypothesis is true, how many standard deviations above the mean is this number? Well, in order to calculate that, we'll take this number, we'll subtract the assumed mean, and we'll divide by the assumed standard deviation, which is approximated by this expression here. This is where we're taking our two samples and we're combining them and making them into one large sample. And that is going to get us from this p1 hat minus p2 hat to a corresponding z-score. And the area to the right of this guy is going to be the same as the area to the right of that guy. Okay, so now we've got p bar and q bar. And with p bar and q bar and n1 and n2, we can just substitute those into the formula. We've got p1 hat minus p2 hat. We've got p1 and p2. We can just substitute everything in, and then we can compute our z-score. So we have z equals p1 hat minus p2 hat. So that's 63 over 322 minus 10 over 310. Minus p1 minus p2, which is assumed to be 0 because we're assuming our null hypothesis is true. And then we're dividing by this expression here. Q bar and p bar are these two numbers. So we're going to have 73 over 632. And then we'll have 559 over 632. And we're dividing by that first sample size, and the first sample size is 322. And then we're going to add p bar times q bar, so those are going to look exactly the same. And then we're dividing by q bar, or excuse me, not q bar, the second sample size, which is 310. So this is going to give us a number of standard deviations above or below the mean. Or we're going to know it's above the mean because that p1 hat minus p2 hat was positive, which means it's above the mean. We're going to say, well, how far above the mean is that? How many standard deviations is that, assuming that this is the standard deviation of that distribution of p1 hat minus p2 hat? So let's use our calculators to figure this out. Actually, this difference in the numerator turned out to be 233 divided by 1,426. So I've got that as my numerator. And then I'm dividing by the square root of the denominator. Or dividing by the denominator, which is this square root. So I've got the square root of, open parentheses for this first expression. I've got 73 over 632 times 559 over 632. So I think I'm just going to do 73 times 559, close parentheses, divided by 632 squared. And I want to take all of that, and I want to divide that by 322. I'm sorry, guys. Somebody is calling here at my mom's house. So now I've got this over here. Okay, so I'm back. So that was this denominator right here, and now we're going to add the second term in this expression under the square root. So I'm going to add this 73 over 632 times the 559 over 632. So I think I'll just take a large set of parentheses for that numerator here, and I'll multiply straight across to make that 73 times 559. Close parentheses for the numerator, and then we're dividing by 632 squared. And then I want to take all of that and divide by 310. All right, so we get 6.42 standard deviations above the mean. That's a lot of standard deviations above the mean. So let's go to MyLab Statistics and see if they like that answer. Okay, so we have 6.42 as our number of standard deviations above the mean. Okay, great. And then we want the corresponding p-value. But remember, if we have a p-value, or excuse me, a z-score that's greater than 3.5, in table A2, that area to the left of that z-score, the z-score that we have, is always assumed to be 0.9999. We can be more accurate by using Excel, but we're going to say that it's basically 1. The area to the left of a z-score that's higher than 3.5 is nearly 1, because the area to the right is nearly 0. Let me show you how to do that in Excel. So if I wanted the area to the left of z equals 6.42, I would type equals norm.dist, open parentheses, 6.42 for my z-score. Then I enter the mean of the distribution, the standard deviation, and true, because we want the area to the left. Now, of course, we're assuming that we have a standard normal distribution. That's why the mean is 0 and the standard deviation is 1. It's giving us a 1 as that value. Now, when I'm asking for the area to the right, which is actually what I want when I'm looking at it, when I'm looking for p-values later, I'm going to take 1 and I'll subtract the area to the left. And they're saying it's 0.0000. So that's one way of doing it. The other option is to use table A2. Let me show you how to do that. So in order to do that, you'd go to your positive z-scores. And if you just keep going down, you see that for z-scores of 3.5 and up, we're assuming that that area to the left is that 0.999 that I accidentally wrote over right there. So I hope that helps you see that our p-value is 1 minus 0.9999, which is going to give us 0.0001. Or if we use Excel to be more accurate, it looks like the area to the right is so small that they're saying that the area to the right is 0. Okay. Now, actually, I forgot when it asked me to identify the p-value to check to see what type of test this is. So let's look at my paper really quickly and look at that alternative hypothesis to decide what type of test. Since we have a greater than sign here, you can think of that as an arrow pointing to the right. In that case, the p-value is the area in the right tail. So this is our p-value. It's the probability of getting a p1 hat minus p2 hat equal to our p1 hat minus p2 hat, or a value that's greater than that. And that p-value, or this area here, is the same as this area here for our test statistic z. And obviously this is not to scale. This is z is approximately 6.42. We're saying, okay, well, what is that p-value? What is that area to the right? And in both cases, we've already computed the area to the right. We said that this was 0.000 using Excel, or we said that this was 0.0001 using table A2. But in both cases, they're very small, especially compared to our alpha value. So let's go back to my lab statistics. Okay, our p-value is 0.000 when we round to 3 decimal places. Okay, and 0 is definitely less than any alpha value. Alpha was 0.01. Since the p-value is less than our significance level of alpha equals 0.01, that means that getting a p hat or p1 hat minus p2 hat of approximately 0.163 is very unlikely given that the null hypothesis is true. It's very improbable given that the null hypothesis is true. So we're going to say if it's highly improbable given that the null is true, but it's actually happening, maybe the assumption that the null is true is incorrect. So we're going to say that the null hypothesis is likely to be false. So we're going to reject the null hypothesis. That's just the rare event rule. Okay, and then we're going to talk about the claim now. Now remember, our original claim was right here. The claim, and I forgot to write it down, was actually the alternative hypothesis. So when we're rejecting the null hypothesis, we're actually supporting the claim. So we will say that there is sufficient evidence to support the claim that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 55. Okay, great. So now we want to do the same thing again, but this time we want to construct a confidence interval. Now, confidence intervals are handled in almost the same way, but we use a slightly different standard deviation. Let me share my paper with you in order to do this. Now, we are asked to come up with a 98% confidence interval, which is appropriate given that the significance level of our one-tailed test was 0.01. So they're asking for this 98% confidence interval, and notice that we're asked to round to 3 decimal places as needed. So I will do this on my paper. Okay, so we want to construct an appropriate confidence interval, and we know that our confidence interval is going to have this form. We're looking for a confidence interval for that difference between P1 and P2. Now, that confidence interval is always centered at our best point estimate, which in this case is P1 hat minus P2 hat. And then we're going to add and subtract some error from this in order to get an upper limit for our confidence interval and a lower limit for our confidence interval. And the error is given by this formula. It's z sub alpha over 2 for the appropriate alpha. That's not necessarily that alpha. And then we're going to multiply by an estimate of the standard deviation. Now, when we're constructing a confidence interval, we're not assuming that the null hypothesis is true. Since we're not assuming that the null hypothesis is true, which means we're not assuming that P1 and P2 are equal to each other, it doesn't make sense to use that pooled sample proportion as an estimate for both P1 and P2. Since we're not making that assumption, the best estimate for P1 and P2 is P1 hat and P2 hat. So in that case, the standard deviation of the distribution of this difference is equal to the square root of this, or is approximated well by this. The standard deviation of P1 is just the square root of P1 Q1 over N1. Now, since we don't know P1 and Q1, we're going to use our estimate P1 hat and Q1 hat when we compute our margin of error. And the standard deviation for P2 hat looks just like it, but instead of having 1s as subscripts, it has 2s as subscripts. But again, we don't know what P2 is, so we're going to use that estimated P2 hat and Q2 hat. And we're using these again instead of those pooled sample proportions because we're not making the assumption that P1 and P2 happen to be equal to each other. So this is the form of our confidence interval. So we take our point estimate, we subtract the error or the margin of error to get the lower estimate, and we add the margin of error to get the upper limit of the confidence interval estimate. Okay, so that's the plan. But again, we cannot just use this alpha from our significance level here. In order to do this, we're going to have to compute a few things. We're going to have to compute P1 hat minus P2 hat. We've actually already done that. We did that in the last segment when we were testing the hypothesis. P1 hat turned out to be 63 over 322, and P2 hat ended up being 10 over 310. And after simplification, getting a common denominator, the calculator did this for us. We got 233 out of 1,426 as our P1 hat minus P2 hat. The question now is, well, what is our error equal to? In order to find the error, we need to identify N1, N2, P1 hat and Q1 hat, P2 hat and Q2 hat, and Z sub alpha over 2. So we already know P1 hat is 63 over 322. Q1 hat is 1 minus this quantity, which is 259 over 322. And P2 hat was 10 over 310. So Q2 hat is 1 minus this quantity. So it's going to be 300 over 310. And of course, we know that the sample size for the first group is 322, and the sample size for the second group is 310. So that's going to be enough. These expressions right here, these numbers here are going to be enough to get us our estimated standard deviation. And then we want to multiply by a certain number of standard deviations. It's going to separate a certain area in the middle of a standard normal distribution from area in the tails. So in order to come up with the right z-score, we've got to think about the hypothesis test that we're using here. So we go back to the alternative hypothesis, and we see that it's a one-tailed test. If we're conducting a one-tailed test with a 0.01 significance level, and specifically this is a right-tailed test, if I wanted to be more specific, I could say that. What this is telling me is that I want the area in the right tail to be 0.01. But whenever you do a confidence interval, you're always looking at that middle area. So if the area in the right tail is alpha equals 0.01, the area in the left tail must also be 0.01. So then the area in the middle, well, if that's 1% and that's 1%, that's got to be the remaining 98%. So when we conduct a confidence, or when we construct a confidence interval, we're going to be constructing a 98% confidence interval, because the area in one tail is 1%, which means that the area in two tails should be 2%, and the area in the middle would be 98% of the total area under the curve. Okay, so the z sub alpha over 2 that we want is not the z sub alpha over 2 associated with this alpha. It's actually z sub 0.01. It's the z-score that separates that bottom 99% of the area from that top 1% of the area. Now, in order to find that, we can either use table A2 or we can use technology. I think I will show you how to use table A2 this time. So this is the z-score associated with an area to the left of 0.99. Let me share my paper with you. Now notice that it's going to area to the left of 99% of the area, 0.99. So it's definitely greater than 50%. So this is a positive z-score. Okay, so now I'm looking for an area to the left of 0.9900. And you're just trying to get as close as you possibly can. And it looks like that's as close as we can get. 0.9901. So this is 0.0001 off from that 0.9900 that we were hoping for. The corresponding z-score is z equals 2.33, because this is 2.30, 2.31, 2.32, 2.33, and the value in the body of the table is giving us the area. So this z-score is approximately 2.33. Okay. So our error value, margin of error, is equal to 2.33 times the square root of P1 hat times Q1 hat over N1 plus P2 hat times Q2 hat over N2. And then we evaluate this. We can use our calculators for this. So I think I'll do the expression under the square root first. This times this is going to be 63 times 259 divided by 322 squared. And then we take that and divide by 322. And that gives us this first quantity. And then I want to add this expression over here. So I'll do the numerator first, open parentheses, and then open parentheses for the numerator. 10 times 300 divided by 310 squared. Close parentheses for the numerator. Oops. And then divide by 310. Okay, so that plus that is equal to this number right here, and we want the square root of the answer. And we want to take that and multiply by 2.33. So we get approximately 0.056564. I'll just round to that many decimal places. Okay, so we've got our error now. And we want to find the upper and lower bounds for our confidence interval. So I want to take P1 hat minus P2 hat. And I want to add the error to get the upper limit of my confidence interval, and I want to subtract the error to get the lower limit of my confidence interval. So we're going to have 233 over 1426 plus the error here, and then we'll have 233 over 1426 minus that margin of error there. So I'm just going to take this value and add P1 hat minus P2 hat, which is that 233 over 1426. And I get about 0.2199. If I round to 3 decimal places, that's going to be 0.220. And then down here, actually, let's subtract that so that we get back to our error. And I want to take this error, multiply by -1, and then add the P1 hat minus P2 hat. So I'll take that and multiply by -1, and then add the 233 over 1426. And I get that value. If I round to 3 decimal places, I have 0.107. So this is telling me that P1 minus P2 lies between this bottom limit, this lower limit, and this upper limit. So that is my confidence interval estimate of the difference between P1 and P2. Let's go to MyLab statistics and see if they like this answer, and then I will show you how to do this with technology. It's actually a little bit faster with technology, just because of the typing and the fractions and all that jazz. So our lower limit was 0.107, and our upper limit was 0.220. Okay, great. Now I would like to show you how to find the exact same interval using Excel. So I will share my screen with you, and this time I'll be sharing Excel. Okay, so if I want to use, if I want to use Excel to do this computation, I'm just going to enter my N1, my X1, and use it to calculate P1 hat and Q1 hat and P2 hat and Q2 hat. So N1 in this case is 322. We had 322 folks over the age of 55. 63 of those dreamt in black and white. So P1 hat is this X value minus this sample size. Similarly, we had 310 people under the age of 25 in our second sample, and 10 of those dreamt in black and white. So P2 hat is that 10 divided by the 310. So now if I want to compute Q1 hat and Q2 hat, all I do is I take P1 hat and P2 hat and I subtract them from 1. So Q1 hat is 1 minus P1 hat, and Q2 hat is 1 minus P2 hat. Okay, and then if we want P1 hat minus P2 hat, it's going to be this value minus this value. So that's our P, or that's our point estimate of P1 hat minus P2 hat. And now we want to find the corresponding margin of error. And we know that the margin of error is given by a formula that looks like this. First, I will find the z sub alpha over 2. And to get z sub alpha over 2, it's actually z sub 0.01 because we are doing a one-tailed test, or it would have been a one-tailed test with a significance level of 0.01. So we had an area of 0.01 in this tail, but when we come up with a confidence interval, it's always symmetric. So if we have this area in this tail, we have to have exactly the same area in the left tail. So z sub 0.01 is the z-score with an area of 0.99 to the left. So what I'll do here is I'll use the normal distribution, but backwards. So I'll type equals norm, and then I want norm.s dot inv for inverse. And what they're asking you for is a probability, or the area to the left. So we want the area to the left to be 0.99, which gives us that z-score of approximately 2.33. This one's more accurate because we're using technology. Okay, great. And then for this expression under the square root over here, I want p1 hat times q1 hat over n1 plus p2 hat times q2 hat over n2, and we want the square root of that. So I will compute that square root, that approximation of the standard deviation. I think I'll call it the estimated standard deviation. That's going to be equal to the square root sqrt of p1 hat times p2, or q1 hat divided by n1 plus, actually, let's put some parentheses in there. I wanted to do the numerator first and then the denominator, plus a p2 hat, whoops, plus open parentheses, p2 hat times q2 hat, close parentheses, divided by the sample size. Okay, I guess it found a typo in there for me. There was a missing parent somewhere. And so yes, that is my estimated standard deviation. And I want to take that and multiply it by this z-score in order to get the error. Not error, but the margin of error. So this is this times this value. And so for our upper limit, we'll have p1 hat minus p2 hat plus the error. And for the lower limit, you want p1 hat minus p2 hat minus the error. And so we get this, and if we round to 3 decimal places for each of these, excuse me, we get exactly the same value or values that we got when we did all that computation by hand. So I recommend that you do it by hand once, just to ensure that you understand the formulas and what you're doing and why. But once you do that, at least once you do that once, you can probably just use technology for the rest. If you can get Excel to do these calculations for you, it's clear that you understand what you're doing, or at least how to use these formulas properly. This class is not about arithmetic, but about sort of coming up with these numbers in the appropriate way and then understanding what they mean. Okay, so now it says, what is the conclusion based on the confidence interval? It says, because the confidence interval limits something 0, do not include 0. It appears that the two proportions are not equal to each other. That's right. Because P1 minus P2 is not expected to be 0 based on this confidence interval. It says, because the confidence intervals, or interval limits, include only positive values, it appears that the proportion of people over 55 who dream in black and white is either greater than or less than the proportion for those under 55. Now, to answer this question, I want to go back to my paper and talk about what those positive values mean for the comparison between P1 and P2. Okay, so I'm looking at this, and this is the proportion of folks over 55. Now, or proportion of those over 55 that dream in black and white. If I want to know how this relates to sub 2, the proportion of those who dream in black and white that are under 25, I can add this P2 to all three parts here. So what we're going to get is P sub 2 plus this number is less than P sub 1, which is less than this number plus P sub 2. So this P sub 1 value is consistently greater than P sub 2. It's between P sub 2 plus this number and P sub 2 plus that number. And of course, P sub 2 itself is going to be way down here. So because this is greater than P sub 2. So P sub 1 is greater than P sub 2. So it would seem that the proportion of people over 55 that dream in black and white is greater than the proportion of people under 25 that dream in black and white. So we'll go down here and we'll say that that proportion is greater than the proportion for those under 25. Okay, great. Last part, it says, an explanation for the results is that those over 55 grew up exposed to media that was displayed in black and white. Can these results be used to verify that explanation? No, it really can't. We can speculate as to the reason why that proportion of people who are over 55 dream in black and white is greater than the proportion for those under 55. We can speculate about that. We have evidence that that proportion is actually greater, but it really doesn't tell us why. There is nothing that we can conclude about why from this hypothesis test. So it says, okay, let's look at options B and C. It says, no, the results speak to a possible difference between the proportions of people over 55 and under 25 who dream in black and white. The results are not statistically significant enough to verify the cause of such a difference. Now, it does not matter how statistically significant the difference is. It doesn't tell us anything about cause and effect. For cause and effect, we need to do an experiment. So let's look at option C. It says, no, the results speak to a possible difference between the proportions, but the results cannot be used to verify the cause. That's our answer. Okay, great. I hope that helps you. I'll see you in the next video to do more examples.